Look at the physical world around us. Temperature, pressure, the intensity of sunlight are continuous phenomena. They slide up and down a seamless, infinite spectrum. But deep inside an embedded system, the STM32 Cortex-M processor operates in total isolation from that physical reality. Its architecture is strictly digital, speaking a language composed entirely of ones and zeros. If you try to feed an analog voltage, say exactly 2.5 volts, directly into a standard digital logic pin, the processor simply cannot interpret it. The voltage falls awkwardly into a gray area between the chip's defined high and low logic thresholds. To make sense of the physical environment, the processor needs a dedicated hardware bridge. That bridge is the analog to digital converter, or ADC. Without this translator, the microcontroller is completely blind to its surroundings. The ADC serves as the sole gateway for environmental perception. Let's follow a physical signal as it hits the microcontroller. Imagine a temperature sensor sending a 2.5-volt signal directly to one of the STM32's GPIO pins. First, we have to configure that specific pin into analog mode in the software, explicitly telling the microcontroller not to expect a standard digital logic level. Once inside, the ADC goes to work. This diagram shows how the converter maps a continuous voltage curve into discrete countable steps by slicing it vertically and horizontally. The STM32 features a 12-bit ADC. That means the hardware is designed to divide the continuous incoming voltage into exactly 4096 distinct levels. If our sensor is sending 2.5 volts, that physical measurement lands on the grid and snaps to the nearest available line, locking in a specific digital value, in this case 2048. This act of quantization forces the infinite variations of physical reality into a rigid mathematical box. It is the necessary first step for all digital processing. The ADC doesn't run on its own. It relies entirely on the STM32's internal clock system to act as its heartbeat. The system clock dictates exactly when and how fast the ADC takes its snapshots of the physical world. This creates an immediate engineering challenge. This plot illustrates what happens when you push the clock too fast. The sample points crowd together, and the resulting recreated line becomes jagged, erratic, and full of electrical noise. Run the clock too slow and your sampling rate drops. A sudden, sharp spike in the original waveform falls entirely between two sample points, completely disappearing from the recreated data. Getting the timing right is crucial. A poorly clocked ADC captures and reports a false reality to the processor. Once the ADC accurately generates that digital value of 2048, where does it physically go inside the chip? We can trace it using this map of the STM32 memory architecture, specifically looking at the peripheral memory region, starting at hex address 40000000. The ADC hardware deposits its translated numbers directly into these memory-mapped registers. From there, it's the embedded C programmer's job to write the code that fetches the data from that precise memory location. Because the microcontroller has limited SRAM, memory optimization is required. We assign this 12-bit reading to a variable sized perfectly for it, a 16-bit unsigned integer, or uint16t. Allocating a massive 32-bit integer for a 12-bit reading wastes the chip's limited resources, but allocating an 8-bit variable truncates the data and destroys the sensor reading entirely. Choosing the correct data type preserves the integrity of the measurement. Now, consider a high-stress scenario where the ADC is configured to sample an incoming signal thousands of times every single second. If the CPU pauses its main logic tasks to manually fetch every single one of those thousands of readings, the system chokes under the workload. To solve this bottleneck, the STM32 uses a hardware feature called Direct Memory Access, or DMA. This network map shows how DMA acts as an independent bypass lane. A steady stream of data packets diverts away from the CPU, traveling directly from the ADC into SRAM storage. The processor can literally sleep while the data is collected. The ADC acts as a deeply integrated, precisely clocked memory-mapped pipeline, built to safely translate the chaos of reality into actionable digital intelligence.